I'm Avi. I work at Stripe, and I'm going to talk a little bit about an open source project that I've been working on at Stripe for the last year or so, Rainier, which is a system for doing Bayesian inference in Scala. Actually, I won't change that slide yet. I am not a statistician. I am not a Bayesian inference expert. This is something I've been sort of coming up to speed on in the last year or so. And this talk really neither assumes nor really teaches you very much about the statistics, right? This is a talk with an engineering hat on. This is a talk about implementation. So there are some other talks actually at this conference that I think go more into kind of the stats side, the application side of Bayesian inference. I know there's one tomorrow sort of along those lines. That is not this. This is going to be much more implementation focused. And so I'm going to try to do my best to kind of motivate the work without sort of, you know, teaching a course on what Bayesian inference is, right? You know, to set up the problem with an engineering hat on, kind of this is, I think, the most salient kind of compressed down into like a couple of Scala interfaces way to think about it, right? We have some objective function. That objective function takes a couple of kinds of input. One of the pieces of input is some data that we have observed in the world, right? This is some values we know. And let's just say that's like an array of doubles. I mean, maybe it's actually a matrix or a tensor or whatever, right? But you know, basically it's an array of doubles. It's a bunch of numbers. And we have some parameters that we don't know the values of. And traditionally, that parameter vector is often represented as a theta. So that's what I've put it in as there. So these are unknowns. And we have some objective function that can take the data and can take a given value for the parameters, right? So we don't know this is the value. We're just speculating what if this were the value. And it gives you back some kind of score. Okay, we're not going to worry too much about what that score means. Just it gives you back some kind of score. And often, people think about this from an optimization point of view, right? So you have an optimizer, and the job of that optimizer is, let's find the value for theta, the particular parameter vector, or if you like, the particular point in the parameter space that minimizes this objective function, right? You know, and often you think of this as, I've got like a regression problem, right? So I've got a bunch of data, I've got a bunch of weights, I've got a loss function, and I want to minimize the loss. I want to pick the weights that minimize the loss function. Okay, so that's an optimizer. There's a closely related thing you might want to do, which is a sampler. So a sampler is not trying to find a single best value of the parameters. A sampler is admitting that we have uncertainty here and is saying, I want to give you a bunch of parameter values, a bunch of parameter vectors, but I want to give them to you kind of proportionally to the objective function, right? So this is kind of fuzzy when we're talking about continuous values, but basically, you know, if you take any bucketing of this stream of parameter vectors, right? And you look at like how many parameter vectors end up in a particular bucket, that should be proportional to if you like summed up the objective function in that, right? Or you can think about it as like integrating under the curve of these spaces or whatever, right? But that's basically what we want to do. So that's the job of a sampler. It's very similar to an optimizer, but admits more uncertainty. So this is a very hard problem to just kind of do in general, right? Because like this could be a very big parameter space and you just search through it, right? How do you do that? So a very common approach to help you with that is to place an additional requirement on the objective function. You say, this objective function needs to be differentiable. And you need to be able to tell me for any point in the parameter space what the derivative of each of the elements, each of the dimensions in the parameter space is, right? And we call that a gradient. And so if you do that, then there are sort of well-known, like fairly efficient ways of doing this problem, right? So in the optimization domain, right, very often we do what's called gradient descent. right? Where basically you just like, you have your point in parameter space, you have the gradient at that point, you move just a tiny bit in the direction of the gradient, and then you evaluate again, and you get a new value and a new gradient, right? And gradient descent just kind of keeps doing that until it finds the, whatever minimum it can find. This is what, if people know deep learning or sort of have heard of kind of all the stuff around deep learning basically makes use of like versions of gradient descent. It tends to use stochastic gradient descent, where you're actually not looking at all of your data at once, because you tend to have a very large amount of data in the deep learning space, right? On the Bayesian inference side, there's an algorithm that's very commonly used that is related to this called Hamiltonian Monte Carlo. I'm not going to teach you all Hamiltonian Monte Carlo, but it's a cool algorithm. Intuitively, the way to think about Hamiltonian Monte Carlo is that if you think about gradient descent as being like, I've got this like valley and I'm dropping a ball and the ball's like rolling down to the bottom of the valley, and that's what I want to find, is like, where's the bottom of the valley? Hamiltonian Monte Carlo, you imagine that the valley is covered in ice and that you have a hockey puck, right? And I'm dropping the hockey puck, and the hockey puck's kind of sliding back and forth along the walls of the valley, and I'm just like strobing, right? I'm just like taking snapshots of like where the puck ends up. And yeah, it's like more likely to be low than it is to be high, right? Because like it's hard for it to climb up the walls, but it's not like it's just going to be sitting at the bottom. It's actually going to be sliding around everywhere, right? And that's kind of, that covers the uncertainty, right? And if it's like a very deep, steep canyon, then yeah, maybe it is just sitting at the bottom, but usually that's not what's happening, right? So this talk, we're not going to talk about the optimization case, which is the case where you have a huge amount of data and you want to find a single point estimate. We're going to be talking about the sampling case, which is generally you have less data and more uncertainty, and so you want to be using a sampler in that case. And we're not going to talk about samplers or implementation of samplers. We're just going to focus on the objective function, okay? On the implementation of the objective function. And the question is, how do you represent it? How do you optimize it? How do you evaluate it? And how do you make it easy to build? So you could write an objective function, and you could do this and use Rainier samplers with it, where you just literally like type out a bunch of Scala code that like takes an array of data and an array of parameters and like gives you back like a value, right? First of all, that's going to be like hard to do super efficiently. You're going to end up doing a bunch of like really ugly stuff, just like the direct array access and making sure to like not allocate stuff, and it's going to be a pain. Second of all, you're going to have to write the gradient for that function, which is at best going to be really tedious, right? So you don't want to do that, generally. So what is commonly done in this space is that you represent the objective function in what's called a compute graph or an expression graph, right? So this is a DAG where you have your leaf nodes that generally represent your parameters. This figure is taken from a recent paper on automatic differentiation, okay? Automatically deriving gradients. So you have a compute graph where you have nodes that represent things like parameters or constant values, and then you have interior nodes that are just operations, right? Like sum these two things, divide them, whatever. You can kind of see how that's going. And then at the very top, you have your output, right? And if you have that compute graph, there are well-known ways to fairly efficiently just kind of mechanically crank through it and produce the derivatives, right? You can, in sort of a single pass through the graph from top to bottom, you can produce the derivative functions for each of the parameters. Again, I'm not going to talk about how that works, but understand that it's like a well-known thing, and it's kind of showing the like derivation on the left there of how that would work, right? So Rainier uses a compute graph, and I'm going to start telling you a little bit about Rainier's design of a compute graph for this. Unsurprisingly, we use like a Scala ADT for this. So we've got a sealed trait, which we call real, because these are all functions. They're real valued functions from some parameter vector of kind of unknown width to a single real value, okay? And there's kind of a little ambiguity when you're working in these. They kind of feel like you're actually working with values, but they're not. They're functions, right? And the two types of leaf nodes are variable, right? We don't know the value of this, or constant. We do know the value of this. And I've put these beautiful visualizations below of these two graphs. One, which is just I created a single new variable and bound that to the variable x, or the value x. And I'm representing with a theta the variable node there. and the other, which is the constant 2. So the one is a function that always returns 2. One is a function that always returns the x parameter, right? It's basically the identity function. And just to sort of, there will be a bunch of these visualizations of graphs. So the little houses represent like basically a variable binding, right? So that's not really part of the graph. It's just like a label, right? And then the other things are like nodes, like objects, Scala objects that are nodes in memory. So let's look at a slightly more complicated. So our graph does also have operations. So for example, it has unary operations. The two most commonly used ones are natural log and e to the x. So we've got like a log method and an x method on real. And any real that you have, any graph that you have, you can take the log of it or take the x of it, and it just creates a unary node, right, that references the previous graph and then has this operation, right? I mean, this is hopefully fairly straightforward for people. And let's look at the visualizations of that, right? So we have our x and our 2 as we did before, and we're going to take the x of each of them, right? So you can see down at the bottom, we have our old x label, which is a direct reference to the x parameter node. And then we have our ex label, which inserts this exp node in between, right? And the arrows, I went back and forth on which direction the arrows should go here. Because people always show compute graphs this way because the arrows are in the direction of the data flow, right? So when I want to evaluate one of these, I get a value for that theta x node, right, for that theta node, and then it flows and it gets, we take e to the x, and then it flows to the output. But this is the opposite of the memory references, right? So when you look at this arrow, you can see that as a data flow going forwards, but you can also remind yourself that what is happening in memory here is that we have a node representing exp that has a reference back to the parameter, right? So anyway, in case people get confused about that, I wanted to point that out. The other thing that's interesting about this is that for the constant, we don't have an exp node, right? And we don't have that because we know what e to the 2 is. And so if we try to take the exp of 2, it's like we don't need to add another node. We can just like compute it right away, right? And in compiler terms, you might think of this as just kind of constant folding, right? It's like, we already know what this is. Let's just do it now. OK. Let's do something just slightly more complicated, which is that we're going to take our e to the x node, and we're going to take the log of that, right? So 2 questions. One, what do you expect that to look like in the graph, right? And very reasonably, I think you might say you would expect to see a parameter node, and then that's connected to an exp node, and then that's connected to a log node, right? That would be sort of the normal thing. Second question, what is log of e to the x? Log of e to the x is x, right? And so that's what we actually get. You can see that the e to the x has the x node, but log of e to the x, we just go back to a direct reference to x, right? So it's doing what I'm calling here an eager partial evaluation. So as you're constructing the graph, if there's some computation it can do, it does it, OK? And this is a design choice that when I talk to people, whether they're like Bayesian stats people or compiler people, they're like, you're doing what? So first of all, why do I want to do partial evaluation? OK, so 2 things to think about with this. One is that we are building these graphs once. We are then running these graphs maybe 1,000,000 times, right? Because we're iterating over this, trying to search through the parameter space. And we want to just crank through this over and over and over again. So it's really valuable if we can do some optimization on the graph at the time we construct it, that we're then going to be able to make use of a huge number of times when we run it. Okay? The second is you're not writing this whole thing as one monolithic mathematical expression. You're going to be using abstractions. You're going to be using building blocks in methods that help you with this. And so for example, you might have a method here. I've got a method up there for the log of the probability density of the normal distribution. And you don't really have to care about why you would want that or what that is. You might already know. But the point is, it takes in like a mean and a standard deviation for a distribution, and then a value that we want to evaluate against that distribution, and it like does a bunch of stuff, right? So I could call that with 3 constant nodes, and it could just spit out the answer as a constant, right? I could call that with the mean and the standard deviation being unknowns, but the x being known. And that would be able to, actually that wouldn't be able to pre-compute anything. I could call it with the x being unknown, but the mean and the standard deviation being known, and then it would be able to like constant fold all of those SD terms, right? But not, not the x minus mean part, right? So to be able to kind of take these, you can think of them as kind of like templates of a computation and specialize them to the particular usage can be very valuable compared to just, sort of always including the full generality of the graph, even when parts of that graph, are already known, right? Why do it eagerly, though, right? So one observation is that theta, the parameters, they change every time, but x does not, right? Our known observations are known. They're not going to change between iterations. And so one design goal for this particular compute graph, because we are working in a space unlike deep learning where the data is relatively small, is often very small, was to allow for the possibility of currying that x parameter, right? We want to end up with a function that is specialized to the data and only actually takes the theta as input, which is to say we're inlining all of our data as constants in the compute graph, right? There's a risk when you do this that your compute graph is going to blow up and become huge, right? But if we have optimizations that protect against that, we want to apply them eagerly so that rather than blowing up into a huge compute graph and then optimizing it down into a small one, we want to just keep it small the whole time, right? We can't optimize realistically kind of doing some crazy whole I mean, we could, but we don't do some crazy whole program analysis every time. Instead, we do what are sometimes called peephole optimizations, where we just look at kind of the local area around whatever's going on right now, but we do it eagerly, right? So let's talk about, yes, Oscar?
You're spending a lot of time on this, which I find interesting, but it seems like, do you really feel like it's like crucial? Because it seems like you could keep it as a totally abstract form to begin with, and whether or not you have a system that runs a pass over it and then applies those kind of combinations afterwards. It seemed like most of what you talked about would be preserved, so it makes me think that I'm missing some deeper aspect of it.
I mean, the thing I can say with certainty is that I found it easier to implement something that was efficient and possible to reason about by doing it this way, right? Someone else might find a clever way of doing it a different way, and that's great, and pull requests welcomed, right? But this was the way that I could get to a working system, and I totally acknowledge there's quite likely path dependence in that, right? I can try to ad hoc rationalize it, right? But right? So because of this crazy path dependence that Oscar is referring to, right? This is the crazy place that I ended up, and let's talk about it, okay? So, you would probably expect that the next thing I'm going to talk about after unary operators is binary operators, right? And here's the crazy thing, is we don't have binary operators. Instead, what we have is linear operators. And what I mean by that is that the node type that we use for addition is what we're calling a line. It's a linear combination, okay? So it represents any number of additions of terms multiplied by constant coefficients, okay? So basically we have a constant vector and we have a vector of graph nodes, and we're taking the dot product of them, and that's the value of that node. And so that lets us represent additions of anything and multiplications of anything by a constant. And then we have the kind of next level up in the rings of that, of what we're calling a log line, for lack of a better name, which is the product of exponentiations with a constant, right? So it's any number of graphs raised to a constant power and then multiply them all. And so that's how we represent multiplications of anything or exponentiations to a constant. And we do have actually one binary node in the system, which is if you want to take a variable and raise it to a variable, but you effectively never use that. It's just there for completeness, right? So what does this look like? So here's a few examples of simple linear combinations. So I've got my e to the x. I'm going to multiply it by 2. Then I'm going to add 1. Then I'm going to add in an x. And then I'm going to add in another e to the x. Okay? And let's see what that looks like. So these are the nodes from top to bottom, right? So first of all, I've got my e to the x. It looks like it always did. And then I've got a line here that just has a single coefficient of 2, because I'm multiplying that by 2, right? That's my 2e to the x. When I add 1, I create a new node, right, that just has another element that's just the 1. It's just a 1 constant. It's not, a coefficient for anything. If I add in an x, I need to add in another element, right, that has the x. And if I add in another e to the x, I don't need to add any new elements. I can just bump the coefficient up, right? So I had 2e to the x, now I have 3e to the x. And the really nice thing about this is it's order invariant. As long as I'm just adding things, whether I have 2e to the x's here and then an e to the x at the end there, or whether I have I'm summing them all together at the front, it can figure out to combine those terms and just have a merged coefficient for them, right? So as long as I can kind of stay in line space, I can keep kind of rolling terms into these coefficients, and that's really nice. What else can I do? Well, so this is another example where I just introduce another variable, right? So I've got y here, and then I end up with I'm not going to spend a lot of time on this slide actually, but I end up with 3y at the bottom and our crazy x thing at the top. And when I merge them, again, it's just you're just merging the vectors, right? You're just merging the elements of the vector. And actually, we do use Scala maps for this. And so even though you don't see it on these, they are sharing structure even in the coefficients, although I don't know how important that is. We can also scale them, right? So if you take an existing one of these lines and you multiply it by a constant, we don't need to create a new node. All that we do is we scale up all of the individual coefficients, right? And so that's what's happening there. So what about nonlinear combinations? What about when we want to multiply stuff, right? So here I've got my function of x, I've got my 3y, and I want to multiply them together. And for good measure, let's multiply another y in there, right? So you can see that we have this other type of node, this log line node, that just has references to those three things. And the coefficients are all 1 because they're all just raised to the power of 1, right? So you can see there's an optimization that it kind of could be doing and isn't, which is that I've got a 3y and I've got a y, and it could be merging that into a 3y squared, but because of the kind of peephole effect, it can't kind of look through the 3 yet to see the y, and so it's not doing that. So I mentioned that as long as you're in line space, it's really nice because you can just kind of keep summing things into it. And in general, the structure of these functions sort of tends to have a huge number of terms that you're summing together, because basically you take log probabilities and normally you have a lot of probabilities you want to multiply. If you have log probabilities, you want to sum them. So anyway, you end up wanting to sum a lot of things. And if we want to sum, if we want to add something to this product, there's kind of a choice that we want to drive this as much as possible towards the output being one of these lines, one of these sum vectors. Okay? And so what it does is it tries to multiply out, tries to distribute all the terms as much as possible to convert this product into a sum, so that maybe the thing we're summing into it is going to just fold into some existing element of the vector. And so when we do that, we get actually this crazy rearrangement of the top of the graph. And you can see that it's taken what was before a single product node, and we want to add something to it. And it's turned it into a single sum node and a bunch of product nodes, right? And you can kind of see the expression before down there to see what's happened is that we've kind of taken this 3y squared and distributed it across the x function, so that now we have some, 6 terms that are e to the x times y squared. We've got 3 terms that are x times y squared, and we've got 3 terms that are y squared, and that all just rolls up into a line, right? So that's nice because now if we have more things we want to add, again, probably we'll come across these terms again, right? There's a decent chance we'll see another y squared somewhere, and we'll just be able to fold this in. And let me show you kind of a simple example of that kind of thing happening, right? So this is, we're taking an L2 norm, right? Like a squared error, similar to that normal PDF we saw before. And so we have, say, e to the x is the parameter that we think is kind of, the mean of something here, right? And we have a couple of data points, 3 and 5, right? So we're going to take the difference between the e to the x and 3 and square it. We're going to take the difference between e to the x and 5 and square it. So individually, those are fairly straightforward. nodes there. You can see there's like the linear x minus 3, and then it gets squared, right? Or the linear x minus 5, and then it gets squared. But if you add them together, it's going to do this thing of expanding it out. It's going to FOIL out the x minus 3, right, to x squared minus 10x plus whatever, 25. And so you end up with a single x squared term feeding into a linear combination. And of course, if that happens for 2 of them, that can happen for any number of them, right? So going back to this idea about folding the data, currying the data in, if this is my loss function, right, and I have an arbitrary number of data points that I'm folding in, I can partially evaluate it all down into this one compute graph of constant size. And so if you think about what that means that the complexity of my iterations just changed. Instead of my iterations each being order n for n data points, my iterations are now order 1. I have order n complexity to build the compute graph, but I only pay that once, right? And this kind of looks like a trick, but it actually does come up in real models, right, that you can do this. And so that's a massive speed up when you can get away with it. So that's the compute graph. Now the question is, how do you evaluate the compute graph, right? So you could build an interpreter, obviously, right, for this thing. That would be very easy. It would be fairly slow. You could try to compile a GPU kernel or something like that, right? One of the design constraints that we had was that we wanted this to be pure native JVM, no JNI libs, no external dependencies on complicated C math libs or anything like that. We're on the JVM, let's use the JVM. So we use the ASM lib to generate Java bytecode for these functions represented by the compute graph. And anytime we're compiling, the first thing we need to do is build an intermediate representation. So let's look at that. So at the top, you have the real compute graph for this function we were just talking about. And below, you have something very similar, but it's the IR. So a few things to note about this, right? One is that we've now gotten rid of the crazy line thing, and we're back to binary operations, right? And that's because the actual machine actually deals with binary operations, right? Another is that instead of having a DAG, we have a tree, right? So the first time that we compute e to the x, we store it somewhere. We store it into a temp variable. You can see it's labeled t0. And then the next time that we come across it, kind of thinking depth first in the graph, we reference it, right? We say, OK, now we have a local variable reference to t0. And you can see that it happens to have made this choice that instead of using t0 squared, it just does t0 times t0, right, which is kind of a small optimization. It also does a useless small optimization, which is that it pulls the 1,000 coefficient out. We had 1,000 e to the x squared, and it pulls that out, factors that out of all the coefficients. There's no reason it needs to do that. If there were multiple things with a coefficient of 1,000, it would actually save an operation for it to pull that out. But it's just being over aggressive, and that's sort of a bug. It's fun to see your bugs turn up in your visualizations sometimes. This is what, by the way, if you generate that bytecode and then you decompile it, right, what the Java code looks like. So this Java code never actually existed. We didn't generate the bytecode by producing Java code and compiling it, just to be clear. But if you throw a decompiler at the bytecode, then this is the Java code that it produces, and you can see it's pretty straightforward, right? You have this function, it takes a params array, and it pulls something out of the params array, and math.x, and stores it in a temp, and then it uses the temp a few times in a very simple math operation, right, and returns it, right? This is just very simple Java code, which is nice because the JIT likes very simple Java code. Okay. Another thing about the JIT, interesting fact. If your Java method gets larger than 8,000 bytes, larger than 8,000 bytecodes, it will refuse to JIT it, and it will be interpreted, and it will be very slow. That is bad. If your compute graph gets large, you might produce a method that is larger than 8,000 bytecodes, and you do not want that. So we have to be able to split these up. So this obviously is not getting close to that range, but we can pretend that we have a smaller constraint and see that we can split it up into multiple methods there that are just calling each other. That's what those like boxes mean. The larger boxes are the methods. And we can see that the main change there is that where we had a t0, we now have a g0. So we're saying this is an intermediate value that is used by multiple methods. So we have to store it in a global. What do we mean by global? What we mean is we do this very simple thing, which is very easy to implement, of just allocating a globals array that we pass in as an extra argument to every one of these methods, and they just use it as a scratch pad. So you can see the highlighted line there. When it computes e to the x, it stashes it in global 0. If any other method in this chain needs e to the x, it retrieves it from global 0. That's all we do. We still only return a single value. It's just kind of this like side channel that we can store stuff into, right? And that turns out to be very effective and lets us split the methods up, right?
Do all of your methods have that signature of params?
All of the methods have that identical signature of double array of params and double array of globals and returning double. Yeah. We also have to split between multiple classes because individual classes can get too big, but it doesn't really matter. It's just like static. It's all static final stuff, right? The other place the globals get used is in gradients. So the gradients have separate methods compiled for them, but almost always, in fact, probably basically always, the gradient needs to refer to intermediate terms that were computed in the forward pass. And so the forward pass will store those intermediate values in the globals array, and then we pass that same globals array into the gradient methods, and they are often like this, look much, much simpler. They're just pulling a few intermediate values and doing some combination of those, and then that ends up being your derivative, right? So is it fast after doing all of this? The comparison point for me is Stan. Stan is a Bayesian inference system, very well regarded, very commonly used by scientists, that has its own DSL that it generates C++ from and then compiles with GCC. Okay? Because of that, it runs pretty fast, right? GCC is very good at generating efficient machine code. Turns out that the Java JIT, if you give it like simple like double operations, is also really good at generating efficient machine code. The advantage that Rainier has is that because Stan does this very slow thing of generating C++ and compiling it with GCC, they do not look at the data because they assume you might run this on like multiple different data sets, right? And so they have to compile it ignorant of the data that they're going to feed through this. Whereas Rainier compiles extremely fast, and so it's really no skin off our back to recompile it every time you give us a new data set, and so we can specialize the compilation to the data. And so what we've seen is that for many cases, this makes us much faster than Stan, right? So we see like a 10x speed up over Stan. On the other hand, the JVM never uses SIMD instructions, approximately. And there's also some like fancy linear algebra libraries that Stan uses that can really optimize like heavily vectorized code. And so we've also seen it go the other way, where Stan is 10 times faster than Rainier. This is all benchmarking's hard, take it with a grain of salt, right? But that's the kind of thing we've seen. I was very happy with this result. I did not go into this expecting to be anywhere near Stan's performance, and so it's cool that this actually worked out. I'm going to really shift gears here, and I'm going to do a quick time check before I do that. So I think we've got about 15 minutes left for me to talk, which is probably pretty good for this. So we're going to start to talk about the functional in the title, right? And I want to talk about modularity, okay? This is my kind of hand-wavy diagram of what deep learning models tend to look like, okay? I was very gratified to see that almost this exact same diagram appeared in Tongfei's talk earlier, if anyone was in that one. So basically, what deep learning models look like is you've got like some layer that creates a bunch of parameters and like combines them with the data in some way, and then those feed into some other layer that like creates a bunch of parameters and combines them with the data in some other way, and then you get out like some prediction, which we're going to call y prime, right? And then you compare the prediction to the labels that you have from your data, and you feed those into some loss function. Right? That's kind of what it looks like. And the salient thing from my point of view about this is that the loss function is almost an afterthought, right? You do all this work without thinking about the loss function at all, and then you can just kind of like layer the loss function on top. And actually, when you're using a deep learning model that you've already trained, you drop that part of the function entirely out, right? It's like optional and stacked on top. And that's great, right? That gives them great modularity properties in all kinds of ways. Bayesian inference doesn't do it exactly that way. Because in Bayesian inference, every time you create a parameter, you have some prior, right? You're saying, yes, this is a parameter, but these are some constraints I want to put on that parameter. I have some beliefs about what this parameter should be that have nothing to do with my data, right? And so your loss function, or you would say a joint density function in Bayesian speak, right? That gets kind of smeared across your whole model, right? Basically, every module, every layer, whatever you want to think about it, has not just contributes some parameter values or transform parameter values or whatever it is feeding forward into the rest of your model, but it's also producing off on the side some part of your objective function that you're going to need to kind of propagate and compute and ultimately add up, and that's your objective function at the end, right? So this is maybe not intuitive, but this has some modularity problems, right? Because you don't really care about that addition to you have to track it, but you don't really care about it. It's like it's just a term that's going to get added in at the end. It can't impact the rest of your model, right? And so the standard way for people to deal with it, this is what Stan does, this is what PyMC3 does, and so on, is to have some global state and to have some side effect where at your module that's creating some layer or parameter or whatever it is, just kind of like plus equals. It's like, oh, here's my objective function, like plus equals this, right? So we can kind of like imagine a world where Rainier does this, right? We have some class that represents a normal distribution, it has a mean and a standard deviation, and I want to just ask it for a parameter, right? Like give me a normally distributed parameter, thanks. So it can create a variable node, right? Great, that's your parameter. I'm going to return that. That's what you actually need going forward. And I'm just going to kind of like off on the side build a little compute graph that computes the like normal PDF of that and like stick it on some globally maintained, like this is my objective function, right? So I don't like that. I think that's a perfectly valid thing to do, but I'm used to a functional programming style of Scala where that is not what I want to be doing, right? So of course everybody knows the solution of that is to introduce a monad, right? So Rainier has the random variable monad. And this is sort of a skeleton version of the random variable monad. So a random variable monad has two parts. It has the value, which can be any type. And that is like the current state of our evolving model, right, is the way to think about that. And then it's got a density, which is a compute graph. And that is like the thing we want to hide from you, right, which is like the accumulation of the objective function kind of off on the side. And so map method on random variable just changes the state, right? Just changes that value. Like if we're mapping, we aren't changing the objective function at all. We're just transforming in some way the state of the model that we're trying to build here. Flat map has a function that goes from our state to a new random variable. And there we do change the objective function, but we change it in this way, right? We take the old objective function from what we started the flat map, and we sum it with the new objective function, the new piece of the objective function that we've gotten from this new random variable, right? So it looks like this. So we create a new random variable with the value, the new state from the new random variable, but the density is the sum of the two, right? And that's basically it, right? Everything else kind of follows from this formulation of the random variable monad. So now we have no side effects. So here's kind of like an equivalent of the previous slide, and it's kind of ugly because I'm just doing like, flat maps without a for notation or anything, but you can kind of get the idea, right? We return from the normal distribution instead of a real, we return a random variable real, which includes within it the density, the normal PDF, and we can transform that thing with a map. We can use a flat map to compose in some new distribution that depends on it, right, and so on, right, whatever we want to do. We also want to be able to combine these things. Again, this kind of follows from flat map, but from a convenience point of view, it's worth pointing out that you can implement zip, right? So you can take two random variables, one parameter over here, one parameter over here, zip them, and get a random variable where your model state is like the tuple of these two parameters. Or you can use a traverse where you take a sequence of random variables and you end up with a random variable that has a sequence, right? So combine and compose these, and every time you do that, you're going to be summing up their log densities, right? You're going to be multiplying together their probabilities in your model. One point to make about this is that one unusual choice relative to like deep learning frameworks about Rainier's compute graph is that it's scalar, right? Usually people do these as tensor graphs. And the problem in a Scala context is that we are not used to working with tensors as data structures, right? We're used to using Scala data structures like sequences and maps and case classes and that kind of thing. And like Tongfei did an amazing job of a typed tensor. But what I was trying to do, because I can have the luxury of doing this with somewhat smaller amounts of data, is to say we're just going to completely use Scala data structures everywhere. And the other interesting thing is that no matter what data structures you use, they all just fall out at the end. Because all of this monad stuff, right, all of these flat maps and zips and whatever else, is actually just running once to construct this real compute graph that has none of them in it. Right? None of the data structures appear in the final iteration code. They're just a way, a sort of idiomatic and familiar way for you to build this compute graph that then gets compiled to like, you know, totally just like doubles and arrays Java code, right? Or Java bytecode. You know, as another piece of this, we have a trait, and this is quite simplified from the actual implementation, but just to give you an idea, called distribution. And here we're getting a little bit more into like the Bayesian modeling stuff that I probably haven't quite like justified enough or set enough context for, but we're getting short on time. So the idea is that you have a distribution object representing things like uniform distributions or normal distributions or beta distributions or Poisson distributions or what have you. And it can do two things. It can hand you a parameter that, you know, your prior is, it has that distribution, or you can fit it against some data. And so below is kind of, you know, maybe the simplest possible like full model, which is in a for notation, right? Which is that I have some mean that I'm saying is drawn from a uniform distribution. I have a standard deviation that I'm saying is log normally distributed, which is to say it's drawn from a normal distribution, and then we take e to the x. And then I'm going to fit that. I'm going to construct a normal distribution with that mean and standard deviation and fit it against some data. And so what I'm trying to do is find what the mean and standard deviation of that data is. Now, of course, you know, this is probably not the best way to do that. There are like other like, you know, closed form ways of doing that. But if you know, happen to have a sampler to throw at it, like this is a way that you can do that, right? So that gives you an idea of what actually using this stuff in practice looks like. And you might notice that it doesn't look that different. I mean, if you've worked with probabilistic models before, it actually doesn't look that different from the way people like write down probabilistic models. It's a fairly natural notation, just using like Scala's like for flat map notation, right? One subtlety that is interesting to point out. So if you've got a diamond situation here where I've got, say, one parameter that then feeds into another parameter, you know, a couple of different parameters, and then those ones come together to make my prediction or something, right? Each of those at the time I created it, you know, has a prior. So the way that I specified this earlier, we would end up double counting that top parameter, right? Because every time we combine something or transform it, every time we flat map, we sum the previous thing. Right? And so if you kind of walk the graph, right, we have two paths to get to that top one, and so we would double count its prior. And so we don't quite just sum. What we do is we have a target object that is kind of a like identity wrapper around a compute graph. And what the random variable actually holds is a set of those, and we union those sets. Right? And so the only thing that achieves is that if we come again to a random variable or something that, you know, kind of was a random variable we've seen before, we don't double count it. The other thing we have the opportunity to do with that target is in the case where we determine kind of just empirically that folding all of the data in is a bad idea, right? It's like we've got like a million data points and they're not reducing nicely to a compact compute graph. We can bail out of doing that and just include it basically as what like TensorFlow would call a placeholder, right? So we have a place in the target to just embed a bunch of like arrays of data associated with variable nodes in the graph and sort of say, you know, to the sampler, like when you're evaluating this thing, you're going to need to evaluate this part of the compute graph over and over and over again with like this data, right? And so it's kind of like a very constrained loop that lets us scale to larger data sizes than we would be able to if we were actually trying to fold always all the data into the compute graph. One last topic, because I seem to have time for it, is when you're sampling, you don't necessarily just want to get out raw parameter values, raw weights. You probably actually want to use those to do something. Maybe you want to use them to make a prediction. And so the better way to think about the signature of the sample method is this bottom one, right? Which is that I have some data, I have some objective function, and I have some sort of prediction function or output function, which goes from parameter values to some value t. That is what I actually care about, right? And when I sample, I don't actually want a stream of parameter values. What I actually want sometimes is a stream of predictions, right? Which can be of any type. And so how do we kind of achieve that in this framework? So we have one more type in here, which is a generator. And a generator is a way to sort of go from the abstract kind of real compute graphs back to a concrete value. And it does that because it has this get method that gets two things. One is a random number generator, because sometimes these things are stochastic, right? And the other is a numeric instance on real, which is to say a way to take a compute graph and get to double, right? In this one context, what is the double value of that real? And we're going to call this generator with a bunch of different, instances of numeric real, and those will give you different doubles for it every time, right? And so we have a sample method on random variable which says, if you have a way to convert my model state here into a generator, then I will let you sample from this, and what you will get out is a stream of the values this generator produces. And also distribution, any distribution like normal, you can get a generator for, right? So let me show you sort of what that means in practice. So this little model that I had before, right? What the model gets out is a random variable with this tuple real for mean and standard deviation. But what I want to get out when I'm sampling is a tuple of double for the actual values of that mean and standard deviation. And so we have implicits that will take kind of any combination of reals, like a tuple of them or a map of them or a sequence of them or whatever, and just map that numeric over them and give us doubles, right? So now we can take this model, which is expressed in terms of compute graph kind of abstract real objects, and get a stream of actually concrete values out of it. Or the fit method returns the distribution we're fitting against. And we can take that distribution and get a generator from it. So that what we're doing here now is doing like forward prediction, right? What people in deep learning sometimes call like hallucinating, right? So we have our distribution of the data, we fit that distribution against our past data, and now we're going to generate more data from that same distribution. And so that gives us predictions, right? And so those are the ways in which a generator gets used. And so I was giving a talk on all of this earlier in the year, and I said something about, this is actually like three monads composing, right? So we have what I believe is the writer monad, which is random variable, wrapping around basically a free monad, because that's basically what the real graph is, right? And also wrapping around generator, which also has like map and flat map, although I didn't show them, and is the probability monad, right? So if you like monads like Oscar does, you got lots of monads, man. We're at time. We have apparently a few minutes for questions. We just cut a new release today with a bunch of the stuff I talked about and other stuff. If you go to GitHub Stripe Rainier, let me know if like the jars aren't actually on Maven Central or something's breaking, because we just cut a new release, and so it's probably, who knows what the state is. But it's up there, and does anyone have any questions? Yeah?
You hinted at something about distribution of these computations. Do you have any sort of opinion on that, or do you guys run it somewhere that distributes it across a cluster?
Yeah, so one of the reasons we wanted to run this on the JVM was that we wanted to be able to really easily run this on like a Hadoop cluster or a Spark cluster without like any deployment hassles. To be clear, any individual model that you're sampling from runs on a single machine in this case. What we wanted to do was parallel inference of like 100,000 different models, independent models, right? And so that's why we wanted to distribute across a cluster. But this does no distributed inference. And in fact, it's a research problem right now to do this kind of thing in a distributed way, right? It's, you know, as far as I know, at least in the scientific community, it's relatively rare to do that. And people tend to just have like single big machines and run it for a long time, right? Yeah.
It seems that all of those things like real is all running on double. So you does not, your framework doesn't support running on ints or bools or.
The objective function, the compute graph, is always doing computations in double space. Yes. The API for things like fit, so we do support the idea of having, say, a distribution that has different types. So you can have discrete distributions. You can compute their likelihoods, right? Your data can be ints or bools or whatever you want. But the parameters are all continuous, right? Yeah.
So are you going to add the ADVI sampler index?
Someone at Stripe has been hacking on a variational inference. So for people who don't know, variational inference is a way of turning the sampling problem into an optimization problem by saying, well, I can approximate the distribution of the parameters with some parameterized analytical distribution and then optimize its parameters. I don't know if that made sense to anyone. But so far, we're pretty focused on Hamiltonian Monte Carlo as the sampler here, and we're, you know, probably if we wanted to do variational stuff, we would just use like TensorFlow or something, right? But you could, and there is someone who's hacking on it in their spare time, and we'll see if that comes to anything. Yeah.
Why are you doing this?
Yeah. No, that's a very good question. There's a lot of like values of if that I could, or this that I could answer that question for. The current application, production application within Stripe of this kind of Bayesian inference is basically cash flow forecasting for our customers, or of our customers rather, which has a bunch of implications for us for managing our own risk, right? And where us having kind of distributions of outcomes that we can then, so the basic framework that I really like of Bayesian inference is you don't have a classifier that tells you what to do, right? Or a model that tells you what to do. You have a model that tells you, here's the distribution of the possible worlds that could exist, right? And then you have a bunch of actions you might want to take. And you say, for each of those actions, if I pair this action with this possible state of the world, is that good or bad? And how good or bad is it, right? What's my utility function? And then if you integrate over the distribution of possible worlds for each of those actions, then you get, you know, what the expected utility is for that action, right? And that, for me, is a really nice framework for thinking about how to make decisions in the face of uncertainty, and has been really valuable for us for these kinds of cash flow problems. So that's kind of why do we want to do this kind of modeling, right? Why did we write our own system to do this? The other production system that is so there's two other production systems that are kind of commonly used for this. One is Stan, which is largely used in science and like has a dependency on generating C++ code and GCC, and it's just like, I've talked to people at Facebook who use it in production and they just like hate the deployment properties of that, right? Or even the like getting a developer up and running with it is just, it's bad. The other is PyMC3, which I think is a great system, but we don't tend to use Python for production systems at Stripe. We use it for like ad hoc model training, that kind of thing, but this had more of the profile of a production system, and so Python didn't feel like it was a possible choice. Also, our early benchmarking was that we could do this much, much faster in a Scala system than PyMC3, and we were doing enough different model inferences that actually seemed to matter for us. The third reason is that I totally overfit on my experience at Twitter with Scalding, which is that like we built this like Scala data flow system that ended up like everyone at the company ended up using, and so of course the correct thing to do in any case is to build your own Scala data flow system for something, right?
All right, we're going to have to stop there. Thank you so much, Avi.